All right, welcome back to another episode of Science with Surback. Today what we're going to be talking about is the change of concentration with time. Now before we get into the details of these notes, I want to outline a couple of objectives. Objective number 1, use the integrated rate law equations to determine the concentration of a reactant or product at any time after a reaction has started. Determine the time required for a given fraction of sample to react, or the time required for a reactant concentration to reach a certain level. Objective number 2, explain the concept of the reaction half-life and describe the relationship between half-life and rate constants for a first-order reaction. And objective number 3, determine the rate law for a given higher-order reaction from the appropriate data. So we start out here and we need to take a little bit deeper dive and a deeper look into each of these reaction orders. We mentioned how to find the reaction orders after you determine the rate law in the last section. And now what we need to be able to do is go one step further into each of these reactions. So a first order reaction is defined as a reaction in which the rate doubles as the concentration of a reactant doubles. So what we can also do with the first order reactions here is we can associate a rate law with this. And that rate law that we're going to have associated with first order reactions is going to be the rate, which is equal to the concentration of that reactant, and A is just a generic term for the reactant. Now, we can do a little bit with this rate law. Remember from the very first part of this kinetics unit that the change in the concentration of A over the change in time, and it's negative because this is a reactant, so we're losing it as the reaction progresses and that reactant is producing those products. But if we have this rate law here, we can associate a term. And I forgot here, I needed the rate law constant here. Very important that we add that. So it's rate equals K times that rate law constant. Don't forget to add that in. Okay, so as we get through this here, like I said, from the first portion on kinetics, we learned about this change of concentration over change in time, and now we can associate this with that rate. So we're going to set this equal to the rate law constant times the concentration, or the rate law. Now, what happens here is this. We go through this process called integration. I'm not too concerned, but it's a mathematical process that manipulates this particular equation. And I'll put this down. So through integration, what happens is we can associate this. We can take the natural log of the concentration of that reactant at a specific time minus the concentration of the reactant initially, and set that equal. We can set that equal to negative K, the reaction law constant, times our T4 time. Now, if we rearrange this, so we're going to rearrange this particular formula right here, we can get the integrated rate law. So that integrated rate law, all we do here is we rearrange this equation here, and when we rearrange it, we get the natural log of the concentration at some specific time equal to the negative rate law constant K times your T for time plus your natural log of the concentration of the reactant that is initial. So again, just breaking this down here, the concentration or the concentration at T is the concentration of the reactant at a specific time. And the concentration of this A sub naught, that is the concentration of the initial reactant, or the initial concentration of the reactant. So now what we need to talk about is the graph of the natural log of the concentration at a specific time versus time. So there's two things that we need to know. Number one, this graph of natural log of A at a specific time versus time is going to produce a straight line with a y-intercept at the natural log of the initial concentration. And the other thing that we need to be aware of is that this particular equation is going to have the slope equal to negative the rate constant, or negative K. All right, so what we mean by this is as follows. So you can see here we have the concentration of CH3NC versus time, and then over here this is the natural log of the same value, same concentration versus time. If it's a first order reaction, we are going to be able to have a straight line. And if we have a straight line of natural log of the concentration versus time, we know it is a first order reaction. So again, natural log of the concentration versus time, we get a straight line, and we know that the reaction is first order, and we can apply all of this business here that is associated with our first order reactions. Okay, so keep all of this in mind. Very important that you have the idea of the integrated rate law and this. If we get a straight line, natural log versus concentration versus time, we have a first order reaction. So second order reactions, a little bit different, but we start out here with the definition. So second order reactions are defined as a reaction in which the rate depends on the reactant concentration to the second power, or on the concentration of two reactions, each raised to the first power. So again, we have this fancy definition, but we can also associate a rate law for this particular type of order of reaction. So the rate law for a second order reaction, we're going to keep it generic here. So we're going to say the rate is equal to K, the rate law constant, times the concentration of your reactant raised to the second power. So remember, we can add multiple products together to get to that point, but we're going to keep it in that simplicity form. Now, again, we can associate this. The change in concentration of A over the change of time can now be set equal to our rate law for second order reactions. So again, we get this set equal to K times the concentration of A squared. And what we can do, again, through this process called integration, which I'm not too concerned for you to be able to know that. I want you to be able to imply the chemistry side of things on the back end here. But through integration, so I'll put this arrow again, so through this process we call integration, we can manipulate the formula here. So we can take this formula, and because we manipulate the formula, what we can do is we can obtain this value here. We can get 1 over the concentration of A at some time t minus 1 over the initial concentration of A, and we can get this all to be set equal to the rate law constant times time. Now, because we've set it up in this fashion, notice here K is not negative. On the first order reactant, K was negative. Now it is not, and that's through that process of integration, which we could get into more detail and depth if you would like to see that later. But we get this formula here, and what we can do is we can rearrange this to make it a lot more useful for us, and we can obtain the integrated rate law. So again, all we do here is we rearrange this, but to get the integrated rate law, or what we obtain once we go through this process, is as follows. So we get 1 over the concentration of the reactant at some certain time is equal to, again, the positive K times T plus 1 over the initial concentration. And what this does, the reason why we are rearranging it, is it makes it really nice to interpret in terms of our graph. And so that's our next thing that we're going to talk about, is the graph of 1 over the concentration of T versus time. But just as a reminder, remember the concentration of A at T is the concentration of A at a specific time in the reaction. And the concentration of A sub naught is the initial concentration of A, or our reactant. All right, so again, what we're going to transition here is the graph of 1 over the concentration of A at a specific time versus time. So we need to be aware of this. This graph of 1 over the concentration at a specific time versus time is going to produce a straight line with a y-intercept of 1 over the initial concentration. And the other thing to be aware of is that this particular graph is going to have a slope equal to positive K, or positive the rate constant. Okay, so what we mean by this, we have this. We have the concentration of NO2 versus time, and in fact this is the natural log of the concentration of NO2 versus time. And then over here on the right hand side, we have a graph of 1 over the concentration of NO2 versus time. So I want you to notice 2 things. Number 1, notice how this graph right here produces a curved line. That is that natural log. Now, if it was a straight line, this would be a first order reactant. But because of these same data points has 1 over the natural log, or 1 over the concentration of NO2 versus time, this produces a straight line. So because this graph, 1 over the concentration of NO2 versus time, this is going to be a second order reactant. So we can identify through data points if a reaction is second or first order. And we're looking for that straight line. So we have one more type of reaction that we need to talk about before we apply this concept, apply these terms to some examples. And that is a zero order, or a zeroth order reactant. So a zero order reaction is defined as a reaction in which the rate whose rate is going to be independent of the reaction concentration. Now again, it's always easier to see this definition in our rate law formula. And so that rate law for a zero order reaction is the rate equals K times the concentration raised to the 0 power. Now, what we can do is exactly what we have done in the past, and we can do this. We can have the change of concentration of A divided by the change of time be set equal to our rate law. Now, what I'm going to do here is I'm going to set it equal to K, and I'm going to do that because, remember, anything raised to that 0 power is going to always be 1. So this is going to be 1 times K, so we can simply put K. Now, through that mathematical process called integration, okay? So if we manipulate this particular formula, we can get a rearranged formula to be as follows. The concentration of the reactant at some specific time t minus the concentration initially of that same reactant is equal to negative KT. Okay? Now we can rearrange this and we can obtain our integrated rate law. So when we rearrange this, we can get the concentration of a specific reactant at some certain time equal to negative KT plus our initial concentration of A. Now, just as a reminder, concentration of A sub T is the concentration of a reactant at a specific time in the reaction. And A sub naught here is the initial concentration of the reactant. Okay, so once more we need to talk about the graph of the concentration A sub T versus time. So we need to know this. This is going to produce a straight line with a y-intercept at the initial concentration, or A sub naught. And then the slope of this graph is going to be negative K, or negative the value of the rate constant. And so we can see that through this graph here. Again, the concentration versus time, it produces this straight line that we see here. And if it's concentration versus time and it's a straight line, we know it's a zero order reaction. Okay, so now I've thrown a lot of stuff at you with second, first, and zero order reactions, and I've talked about the graphs and the integrated rate laws. Now it's time to see this firsthand in what we can do with an example problem. So what we're going to do here is we're going to use that knowledge of the graphs that we've just obtained, and we're going to be able to determine what the order of the reaction is. So we have our example problem here. It says the following data was obtained from the decomposition of nitrogen dioxide at 300 degrees Celsius. We have this reaction here, and then we also have the time and the concentration of NO2. Now I'll give you a hint here that this is either going to be a first or second order reaction. And so the way that we have to do this is we have to set up a graph that shows us the natural log of the concentration versus time for a first order reaction. And then we have to do the same thing for 1 over the concentration of NO2 versus time. So what we're going to do first is this. We're going to, quote unquote, get the first order reaction graph. And remember, if this is a straight line, so if this first order reaction graph is a straight line, then that means that the reaction is first overall order. If it's second order, or if this graph over here is going to get us a straight line, it's going to be second order. So the first thing that I want to identify is our x and y axes. So our x-axis is going to be the natural log of the concentration of NO2, and then our y-axis is going to be the natural log of the concentration, and then our time in seconds is going to be our x. So what I'm going to do over here is as follows. I'm going to put the natural log of the concentration of NO2, and I am going to obtain these values. So all I'm going to do is put the natural log of NO2 in each of these categories. So I'm going to have natural log of 0.01, and I'm going to press enter, and that gets me a value of negative 4.605. So negative 4.605. And then I'm going to do the natural log of 0.00787, so 0.00787. I get a value of negative 4.844. Negative 4.844. Then I'm going to do the natural log of 0.00649, and I get a value of negative 5.037, so negative 5.037. We'll do the natural log of 0.00481, and I get a value of negative 5.337. And then I'm going to do the natural log of 0.00380. Okay, and I get a value of negative 5.573. So negative 5.573. Now what I'm going to do is I'm going to graph. These are going to be my data points that I put on this graph. But before I get to that point, I want to talk about units. So notice here we have negative, and these values are pretty small. So I'm actually going to do this. I'm going to work my way up, and so I'm actually going to start here at negative 5.8, and I'm going to go up, and I'm going to have negative 5.6, negative 5.2, and actually we need to go by 4/10. Let's go negative 4 or 5.4, negative 5.0, and negative 4.6, and negative 4.4. So what we're going to do, we're going to plot our points, and I should decide on the time. Let's do each line. Each line is going to be 50 seconds. So the first one will be 50, the next one will be 100, 150, so on and so forth. So what we'll do here, and I know this isn't written very well, but that is negative 5.4. Okay, so we're just going to plot our points. So we're going to put 0 as our x point here, and negative 4.605. Okay, so this would be right about here. All right, then we're going to go to time equals 50 and negative 4.844. So this plot would roughly be about here. And then we're going to go to 100, negative 5.037. So 100, it would just be negative 5.037. 200, we got to be careful on our graph. We're going to go to negative 5.33. So 200 would get us a value right here. And negative 5.33 is roughly about here. And then we get 300 seconds, and that value is negative 5.573. So again, estimating this is going to be negative 5.5 will probably be here. Now, it's hard to see this, but we have, and I'm going to exaggerate this a little bit, we have this. This, you can't see it very much, is a curved line. The only way a reaction can be first order is for this particular graph, natural log concentration versus time, to be a straight line graph. Let's go over and let's do another plot here. Let's do 1 over the concentration of NO2 versus time. So what we're going to do on this graph, and this is going to be our second order graph, is we're going to go through this process here. We're going to have on this 1 over the 1 over the concentration of NO2 versus time. Okay? So we need to find the values of 1 over the concentration of NO2. So we go 1 over 0.01, and that gets a value of 100. We do 1 over 0.00787, and we'll get a value, we'll say 127. We'll do 1 over the concentration there, 0.00649. We get a value of 154. We do the next one, so 1 over 0.00481. We get a value of 208 when we round. And then we do 1 over 0.0038. So 1 over 0.0038. And we get a value of 263. Okay, now we're going to decide on our units, and we're going to start at 50. And let's go ahead, we'll go up by 25. So this would be 75. This right here would be a value of 100. We would get a value of 125. And then we would get 150, 175, 200, 225, and so on. So over here we'll have our time, and we'll again use 50 as our value. So 50, 100, 150, 200, 250, and then 300. Okay. All right, so we plot our points here. We start out with time at 0 and 100. So we are going to start out with our first dot right here. Now, our next dot would be at 50 and 127. So 50 and be about right here. And then we would go to 100 and 154. So again, this would be right here. And then we'd go to 200, 208. So 200, 208 would be about here. And then this would be off our graph here, but 263 or 300, 263 would be here. Now, check this out. Look at all these points, all right? Look how this makes a really nice straight line compared to this one. Remember, I had to make a little curved line. But because this is a straight line, because the graph of 1 over the concentration of NO2 versus time is a straight line, this means our reaction here is second order. So let me pause and I'll write that down. All right, there we go. It's explained very well here. Since the graph of 1 over the concentration versus time is producing this straight line, it means the reaction is second order. What that means is we can actually write the rate law of what we have here. So what we have here, we could write the rate law. So the rate would be equal to K times the concentration of our only reactant, which is NO2. So NO2. And that would be raised to the second power because that is a second overall order. All right, so that was the whole point of finding or talking about the graphs. Whatever graph produces a straight line is going to determine what the order of the reaction is. So as long as we have lab data, we can determine what the reaction order is. Now I want to go into a little bit more of an application of what we can do with these orders, and that application is the half-life. Okay, so an important concept here that kind of stems from those integrated rate laws is this concept known as half-life. And half-life is defined as the time required for the concentration of a reactant to decrease to half its original value. Now, because we had some different integrated rate laws, we're going to have some different half-life formulas depending on the order of the reaction. So the first formula that we're going to talk about is for a first order reaction. Now the formula for the half-life is going to be T for time, and we put this sub half to represent half-life. The half-life, the time required for the half-life, is going to be 0.693 divided by K. Now, I'm going to leave a little bit of room, and that's because I want to talk a little bit more in depth and in detail about the time required for the half-life, or how we got to that formula. But we'll move down here to the second formula, which is for a second order reaction. And for a second order reaction, the half-life, so T sub half, the time it takes for a half-life to occur, is going to be 1 over K, the rate law constant, times the concentration of the original amount, all right, or A sub naught. Now, I'm not going to leave a whole lot of room here, but I'm going to talk next about the zero order reaction. And the formula for half-life for a zero order reaction is our T, so our half-life time, is equal to the original concentration, so A sub naught, the original concentration, all divided by 2K. Okay? Now, I want to go back up to our first order reaction, and I want to use the integrated rate law to be able to get to this particular formula. So let's remember this, that the integrated rate law is the natural log of the concentration at some time t is equal to the negative kt plus the natural log of the original concentration of your reactant. Now, let's think about the concept of half-life. It says in our definition, the time required for the concentration of a reactant to decrease to half of its original value. So let's say our original value, our A sub naught, our original amount of A, is 1.0 molar. Well, if we decrease to exactly half, then our concentration at the half-life would be 0.5. So the concentration of the reactant after a half-life would be 0.5 molar. Okay? So now I'm going to plug those things in, and I'm going to solve for T. So I have the natural log of A. I have the natural log of A sub T, which I just told you was 0.5. So I'm going to put 0.5 in these values here. And this is equal to negative KT, which we're going to solve for T. And then we put plus the natural log of our starting concentration, which is 1.0. Okay? So in my calculator, what I'm going to do is I'm going to put the natural log of 0.5. So natural log 0.5, press enter, and I get negative 0.693. So I'm going to write that down. Negative 0.693 equals negative KT plus the natural log of 1. So the natural log of 1 is 0. Okay? Now what I need to do, I'm going to rewrite this right here without the 0. So I'm going to have negative 0.693 equals negative KT. I want to get T by itself. So I divide by negative K on each side. And so my half-life, this is where we get our formula for half-life, is this, T sub half. And that's because we went from 1 to 0.5, half the original concentration, for a first order reactant is 0.693 divided by K. That's how we were able to obtain that formula. Okay, so this formula for half-life comes directly from that integrated rate law. Now we could do similar type of things for second and zero order reactions, but we have to manipulate it a little bit differently, and I'm not too concerned. All I wanted you to see is, hey, this half-life formula comes from that integrated rate law in some way, shape, or form. Now, I want to make this statement about our first order reaction, and that is this. the half-life in a first-order reaction is going to remain constant throughout the reaction. Now, in a second-order reaction, I want to make this statement here. The half-life depends on the initial concentration of the reactant, and thus, the lower the initial concentration, the longer the half-life. Again, I kind of squeeze this in here, but for a second-order reaction, the half-life depends on the initial concentration of the reactant, and what happens here? The lower the initial concentration, the slower the half-life. And so the last statement I want to make here about the zero-order reaction. So for a zero-order reaction, the half-life will get faster each and every half-life. Each half-life will be cut in half for a zero-order reaction. Another way to say this here is that each half-life will become 2 times faster than the last half-life, or it will double in speed. So you'll reduce your half-life as the reaction progresses. Okay, so let's use some of these half-life formulas in a few examples. All right, so we have an example problem here as follows. So we have chlorobutane is a first order reaction. We need to use this data in this chart to be able to calculate the time of each half-life and the rate constant. So the first thing that I want to identify is this. We get told that this is a first order reaction. So we know that the rate law, so rate equals our K times our C4H9Cl raised to the first power. But we also know the integrated rate law. And this is probably more important for us in this aspect here. So remember the integrated rate law, I'm just going to write it below, is the natural log of A sub t is equal to negative KT plus the natural log initially, or that initial concentration. So now what we need to be able to do is we have to solve for K. So we're wanting the half-life as well, so we can knock a couple of things out. Number one, let's go ahead, let's solve for K. So our whole goal here is going to be to solve for K. And the way we need to do this is we need to pick out times where our value of chlorobutane decreases by half. So we start out here, if you look on the graph, we start out here with 0.100. So initially our value for A, our initial value is going to be 0.100. Now, think to yourself, okay, what is half of 0.100? And if you don't know, don't be afraid to get out that calculator. Half of 0.100 is 0.05. So we need to find on our chart, do we have a value for 0.05? Well, we do. So let's go ahead and make our concentration of T 0.050. Now, the last thing that we need to do before we go solve for K is we need to find out, well, how much time went from going from 0.1 to 0.05, okay? Well, the time it took to get half of our original value was this. We find that point there of 0.5, and we go down. Well, 0.05, if we follow this all the way down on the graph, looks like it took 350 seconds. So the time here is going to be 350 seconds. Now, what we need to do is we need to solve for K. So we'll put in this. The natural log of our concentration at the specific time was 0.050. So 0.050 is equal to our K, our negative K. We don't know what it is. Times our time, which is 350 seconds, plus the natural log that we initially started with, which was 0.100. Okay, now what I'm going to do is I'm going to calculate this. Natural log of 0.050 is equal to negative 2.996. So negative 2.996 is equal to our negative K times 350. We'll get to that here in a second. And then we have plus our natural log of 0.10. 0.10. There we go. So we get a value of negative 2.303. We need to get rid of this negative 2.0303, so we have positive, or pull that plus 2.303 on both sides. Now, our value here is this, negative 2.996 plus 2.303, and we set that equal, and we get a value of negative 0.693, should look familiar, is going to equal negative K times 350 seconds. So the way we're going to get K by itself is we're going to divide everything by negative 350 seconds. So we're going to take negative 0.693, so negative 0.693 divided by negative 350. And we get a value of 0.00198. Now, most often we're going to express our K, or our rate constant, in scientific notation. So our K, because it's a first order reaction, I'm going to write this underneath the graph. Our K is going to be 1.98 times 10 to the negative third molar per second. Remember, we went over units, how to obtain that for a 0, first, second, and third order reaction. So that's how I know my units. Now, we haven't quite got to what our answer is. We need to figure out the half-life. So the half-life is going to be constant because it's a first order reaction. So we're going to have 0.693 divided by our K. So we're going to insert those values. So 0.693 divided by 1.98 times 10 to the negative third. Okay? And when we do this here, it would give us a value of 0.693 divided by 1.98 times 10 to the negative third there. It gets us a value, a half-life of 350 seconds. So each and every half-life is going to be 350 seconds. And remember, this was molar per second, so that's where we got our value for seconds. All right, so those two things become our answer to this question here. Now we can move on. And answer one more question. All right, so we're given the following. We are given the K this time, and all of a sudden we want to know what is the concentration of NO2 after 2.50 minutes if the initial concentration of NO2 is 0.1. Well, you may be thinking, okay, I don't know the reaction order, but we actually do. Remember from our units, we talked about our units, and this is the units of K become really, really important. I'm looking at this. This inverse second tells me a heck of a lot about this particular reaction. This inverse second, or this unit for K, is going to tell me the reaction order. And I know just from memory, and you can look it up in prior notes, I know inverse second means that this is a first order reaction just from the unit of K. And it's really important to understand what the units of K are and how to remember that. So now we can do a lot of things here. We can put down the integrated rate law for a first order reaction. So that integrated rate law, once again, for a first order reaction is the natural log of A sub T equals negative KT plus the natural log of that initial concentration of A. We have a lot of information. We want to know what is that concentration after this time period. So our A sub T is actually going to be our question mark. It's going to be what we're finding. Now, our K is given. So our K for this particular problem is given in the problem. So it's 3.6 times 10 to the negative third inverse seconds. Our T is in 2.5 minutes, but look at our unit for K. It is inverse seconds. So 2.5 minutes needs to be converted to seconds. So remember, 1 minute, there is 60 seconds. So if you take out your calculators, you have 2.5 times 60. You press enter, and we have a value of 150 seconds. And then we have our initial concentration of A, which is given in the problem at 0.10 molar. Okay? Now, we plug all of this business back into our equation. So we are going to get the natural log of A sub T. We don't know what that is. Equals our negative, and I'm going to put this in parentheses, 3.6 times 10 to the negative third inverse seconds, times our time in seconds, which is 150 seconds, plus the natural log of our initial concentration. So we have a lot going on here, and here we go. All right, so we have negative 3.6 times 10 to the negative third times 150. I'm going to press enter. I'm going to multiply, or I'm going to add the natural log of 0.1 to our value here. And we get a value of negative 2.843. So the natural log of A sub T is equal to negative 2.843. Now, what we need to do is this. We need to get rid of this natural log business. So if you check out on the calculator, the natural log of the inverse of natural log is e to this x button. So we're going to take both sides by e to the x. That will eliminate this business here, and it will allow us to just solve for the concentration at this specific time. So what we have here is this. We're going to put inverse, so e to the x, and we're going to put negative 2.843, so negative 2.843. We're going to press enter. We get a concentration of 0.0583. So we get a value, and we could actually round that to two significant digits. So we get a value of 0.058 molar for our concentration. So after 2.5 minutes, only 0.058 molar remains. Now, we have a problem here. It says, hey, how long would it take for 99% of NO2 to be consumed? So what we first need to do is this. If 99% is consumed, we need to take 99% away from our starting concentration. So what we're going to do is this. To find out our value for the concentration at one specific time, we're going to have to use 99% and this 0.1. So since that's the first variable listed, let's go ahead and do that. So the concentration at the specific time is 99%. So what we need to do to find 99%, if 99% has gone away, we need to take 0.1, because that's our original concentration, and we need to subtract it from 0.1 times 0.99. And so when we do this, we get 0.1 minus 0.1 times 0.99, and we get a value of 0.001. So 0.001 is going to be our A sub t. Now, our K, I'm not going to rewrite this, but our K is going to be the same. It's going to be the same constant. Our T is what we are going to be solving for. So our T becomes our question mark, and then our starting concentration is still the same at 0.1. Now, let's go ahead. Let's put K there just so we know where K came from. So 3.6 times 10 to the negative third inverse seconds. And then what we're going to do here, we're going to plug this in. So we're going to put natural log of 0.001 is equal to negative 3.6 times 10 to the negative third inverse seconds times your t, your time, plus the natural log of 0.1. Okay, so what I'm going to do in my calculator, I am going to put natural log of 0.001. I'm going to press enter. I get a value of negative 6.908. So negative 6.908 is equal to negative 3.6 times 10 to the negative third inverse seconds times t, plus the natural log of 0.1. So the natural log of 0.1 is negative 2.303. Negative 2.303. I'm out of room. I don't want to squeeze this business here, so I'm going to grab another sheet of paper. Okay, so I'm just going to copy down what I have right here. So we have negative 6.9908 is equal to negative 3.6 times 10 to the negative third inverse seconds times t, plus a negative 2.303. We're going to get rid of this 2.303 by adding 2.303 to each side. So we'll add 2.303. So negative 6.908 plus 2.303. Whoop. Negative 6.908 plus 2.303. We get a value of negative 4.605. So negative 4.605 is equal to negative 3.6 times 10 to the negative third inverse seconds times t. To get t by itself, we divide by whatever it is attached. So negative 3.6 times 10 to the negative third inverse seconds. And we're going to divide that on both sides. So I'm going to keep this in my calculator. So negative 4.605 divided by negative 3.6 times 10 to the negative third. And I get a value. I'm going to round to, let's see, I used 2 digits. So you could round to 1,300 seconds. In our calculator, it would be rounded. We could round to 1280 seconds equals time. if we're thinking about sig figs, it would actually round up to 1,300 seconds as our time. All right, so that has been a lot. Remember, the graphs tell us a lot. If we find that straight line, we can determine what the order of the reactant is. Once we know the order of the reactant, we can apply the integrated rate law to that particular problem. Hope you have enjoyed this episode, and if you haven't already, make sure you subscribe.